Hi and welcome to my video on map projections. First, we'll consider that the Earth is a globe because it is. No flat earthers. If you're a flat earther watching this video, it's just gonna be 30 minutes of pain, okay? The Earth is not perfectly a globe, it is oblate, but this is minimal, just 0.33%. So for the purposes of this video, we're just gonna imagine that the Earth is perfectly spherical. When we're talking about polar coordinates, we're talking about longitude, which is defined with the symbol lambda, and latitude, which is defined with the symbol phi. A latitude of 0 is the equator, and a longitude of 0 is the prime meridian. When the angles go on the right or on the top, they're positive. When they go on the left or on the bottom, they are negative. Example, this 180 here is negative. It would be negative 180 degrees. Latitudes and longitudes will vary from these values, but for the rest of the video, we are going to be using radians. One simple way to convert polar coordinates into scalar coordinates in 3D spherical geometry is using this substitution. Now, how do we calculate the distance between two locations on the globe? We're going to be using the locations of New York and Paris. Here on a 3D calculator, I've drawn in the prime meridian, the equator, and Paris and New York. First, we'll convert the 3D polar points into scalar points and then into scalar vectors. So we use this substitution. We've converted it into scalar points and now scalar vectors. Now we need to calculate the angles between the two vectors. There is a simple one-size-fits-all formula for calculating the angle between two vectors, and once we apply it, we get this. And now in order to calculate the distance between those two cities, what we actually need is the arc length, which in radians is just the angle multiplied by the radius. So this is the formula. We've multiplied here the radius by the angle, which is generated by this function. And now as an example, we can use Paris and New York and the radius of the Earth. Our calculated distance using this formula is 5,837. Meanwhile, the real distance, if you look at a commercial flight, will be this. The reason why the real distance is a little bit higher is because the plane does fly above the surface, not directly on the surface. And also the Earth is oblate, and I'm sure the commercial flight takes this into consideration. Now we're going to calculate the route between two locations on the globe. What this means is we're going to calculate every single finite point in that trajectory. And that specific route is the shortest route possible. The way we do this is first we take our two vectors and do a vectorial product, which gives us a normal. And now we use the normal to make a plan that passes through both points. Just by doing these substitutions is how we make the plan. As you can see, x, y, and z are all substituted down here to make the plan. Now we're going to make our trajectory point generator. The way we do this is we calculate how the plan intersects the globe. And every point where the plan intersects the globe is part of our trajectory. So we use the formula of the plan and we substitute our coordinate to polar formula. And now once we isolate phi, we get our polar coordinates trajectory point generator. We're going to simplify it a bit more. If you calculate these constants, you can actually simplify it. These are the exact same things, they're just simplified. If you don't know what arctan of something semicolon something means, if you've never seen the syntax, it's the same as the argument, or it's the same as having a point, drawing a vector to that point, and taking the wide angle that is counterclockwise starting from the x plus axis. Now we have our route, and the exact parametric formula for the route is this. So before we start with all of the map projections, I'm going to do a quick shout out. I am crediting the creators, and here are the licenses. I have the right to use these pictures if I show the licenses. When it comes to the map projections, the first, easiest, and simplest one is the orthographic map projection. The orthographic map projection is basically a picture of the spherical globe and you end up with a circle. It is basically what happens when they take pictures of the Earth in space. This is the oldest map projection. The further you venture off from the middle, the more compression you're gonna see, and the more shapes get compressed and distorted. This is Desmos and Desmos. This is the formula for the orthographic map projection. This is the formula for the trajectory. The trajectories themselves are actually two functions that trace an ellipse. The shortest path is the one that's visibly the shortest. If you take the other path, that's actually mathematically the longest path. And so it starts here and then it actually goes to the back of the map, which isn't projected here because the orthographic map projection most of the times only projects one half of the Earth at a time. So it goes behind the map projection here, and then it comes all the way back to the front. That in blue is the longest mathematical path between those cities. And the way we calculate the trajectory function is we isolate lambda and phi, and we substitute them within the point generator. And then here, this point generator, as we can see, it is not a function, it is a formula. So once we isolate y, we can create a function which shows the trajectory. Just a reminder of how to calculate u and v. This is what it looks like overlaid over an actual map projection. Now comes the equirectangular map projection, what I believe to be mathematically the easiest map projection. This is what it looks like. Now there is some distortion. The further away you go from the equator, you'll find distortion. The neck of Alaska is stretched. That's the distortion you'll find within this map, is objects being stretched left and right. Here, Greenland looks stretched and Siberia looks stretched. You can see it in Desmos and Desmos here. Not only is it stretched, but the areas aren't preserved. The reason behind that is that on the globe, the biggest parallel is the equator. As you go away from the equator, the parallels get smaller. Meanwhile, on the map projection, every parallel is the same length. So that's why as you go far away from the equator, the map gets stretched because it doesn't have the compression that it is supposed to have. And once again, we calculate the trajectory by taking lambda and phi, inputting it in the point generator, and then that gives us the trajectory. The reason why I said mathematically this is the easiest map projection is because it's just a multiplication. We just take lambda and phi and we multiply it by the constant of the radius, and that's it. This is what it looks like overlaid with the trajectory. Now comes the central cylindrical map projection, what I believe to be the ugliest map projection, but it does have one quirk. The idea behind it is that you take the globe and you project it into a cylinder, and then you unroll the cylinder into a map. But you will notice that you would need an infinitively tall cylinder. So this map projection doesn't project the entire Earth. There are cutoffs. And as you can tell, if you draw a cylinder and you calculate the height of the cylinder, you're essentially looking at the tangent, which is why, this is what it looks like. And you can see that it stretches up and it goes up to infinity, and there are cutoffs. There's parts of Greenland missing, and you can see how Antarctica is stretched like crazy. And you can see how the areas are not preserved. As I showed earlier, the y value is simply tangent because of how the map projection is made. The one quirk of this map projection is that the trajectory is a simple sine wave. Now comes the Lambert cylindrical map projection. The idea behind this one is, once again, we project the sphere into a cylinder and then we unroll the cylinder. But the previous one would have gone like this, up to infinity. Meanwhile, this one goes horizontal the moment it touches the globe. We can tell that this is basically a sine wave. This is how the map projection looks. It is an equal area map projection, which means whilst the shapes may be distorted, the areas are equal. So Greenland proportional to Africa are correct. You can tell that the areas are preserved because whilst the shapes are distorted, this very stretched oval is actually the same area as this circle. Like I showed earlier, the way that the map projection is defined is through a sine wave. And the trajectory function is this. And this is what it looks like overlaid. The Gauss-Peters map projection is a very popular map projection, but I'm not going to talk about it for long because it is exactly the same map projection as the Lambert cylindrical map projection, just stretched and compressed to have a different aspect ratio. That's the only difference, different aspect ratio. This is what it looks. And because the aspect ratio was changed, even close to the equator where Africa is, there is significant distortion, but the areas are preserved. These circles in the middle are the same area as these very stretched thin ovals. And now we come to the sinusoidal map projection. Now, if you remember the equirectangular map projection, it was stretched because the parallels didn't get smaller as we got closer to the poles. Well then, the sinusoidal map projection asks, why don't we just compress the map as we go to the poles so that every parallel is the exact same length on the map and on the globe? So the radius of the parallel is small r, which is equal to big R, which is the radius of the globe, times cosine of phi. What we do is we multiply by cosine on both sides, and that will compress the map into an equal area map. And it gives you this. This map projection is equal area, and you can tell because Greenland, respective to the size of Africa, look how they look on the globe. Another property of this map projection is that all of the horizontal lines are proportional on the globes. If you draw two horizontal lines of the same length on this map projection, they will be also the exact same length on the globe and in real life. Although the one type of distortion that this map projection does experience is rotation. The best example of that is the northern part of Canada, which is quite tilted, or Russia, or Australia, which is quite tilted. It does experience what I like to say is tilt distortion. We can interrupt the map projection so that there's less tilt, but the more you interrupt the map projection, the more impractical it becomes. Here's Desmos and Desmos. Even though it does look like the circles aren't the same area, they are mathematically. It's more of an illusion. Whilst this oval is longer, it is also thinner. This is the formula for the sinusoidal map projection, and the trajectory for it is a mess because it is implicit. We have y here and we have y here. And this is what the trajectory looks like. As for the Mercator map projection, even though this map projection does have one massive drawback, it is by far the most important map projection. For one reason, it is very practical when using rhumb lines. Now you may ask, what are rhumb lines? Let me explain. Rhumb lines are basically lines where the angle on the line from the pole to the rhumb line is always the same. You can think of it this way. If you had an ideal compass that points to the geographic North Pole, it would always point at the same angle as you move along the rhumb line. Now, the reason why I have a parenthesis is because compasses in real life actually point at the magnetic North Pole instead of the geographic North Pole. The difference is the geographic North Pole is the pole tied to the axis of rotation of the Earth, which doesn't change and hasn't changed since the creation of the Earth. Meanwhile, the magnetic North Pole does change every few centuries and is offset and different from the geographic North Pole. So the parametric function for a rhumb line is this. If you're wondering what these parameters are, t is the parametric parameter. Meanwhile, lambda at phi equals 0 is basically the longitude at which the rhumb line hits the equator. What we're going to do is take our scalar rhumb line formula and convert it into a polar drumline formula. So the way that we do this is we just substitute our old scalar to polar equations into the mix, and then with a little bit of math, we get a polar formula for the drumline. First of all, there's two common ways to describe the Mercator map formula. They are exactly the same. So that's the first thing I'll just prove, that these two ways of describing it, even though they look different, they are the same. And this is the math to prove that, if you want to look at it. Now that we have our drumline formula on the globe, which is a polar formula, we're going to do these substitutions to get a drumline formula that is still polar, but it depends on A and K. By changing our drumline formula to depend on A and K, we can prove that the Mercator map projection always has drumlines as linear functions by doing these substitutions. The way it really works is the drumline goes like this, and then as it goes off the map, it continues like this. And so the drumlines last till infinity, but on a Mercator map projection, they are all linear functions. And this is how they are defined. So this is what the Mercator map projection looks like. The areas are not preserved, the map is distorted, and there are cutoffs, but all of the shapes and all of the angles are preserved. Whilst Greenland looks bigger than Africa, this is actually the first map in all of the map projections that we've seen that actually doesn't distort the shape of Greenland. It distorts the size, but not the shape. That's the thing with the Mercator map projection. As you can see, the circles are not equal area, but their shape is conserved. This is the formula for the Mercator map projection. For y, you can either use this formula or this formula. Although do not use this, I see this on the internet that they define the Mercator map projection like this. This is false. This is a misunderstanding of what the map projection does. The point generator formula is this. And the trajectory function, now this is not a drumline, this is a trajectory, is defined like this. The drumline on a map projection, the polar formula is this. Although if you draw any linear function on a Mercator map projection, it is a drumline that matches this polar formula. And this is what the trajectory, not the drumline, the trajectory between New York and Paris looks like on the Mercator map projection. As for the Molly-wide map projection, this is probably one of the best because it looks aesthetic, yet it preserves the areas. But mathematically, it is quite difficult to calculate. This is the Molly-wide map projection. It looks very aesthetic, and it is an equal area map projection. You can see it with Greenland and Africa, although it does suffer from a little bit of tilt like the sinusoidal map projection, as you can see with Australia. It is noticeably less. As for the Molly-wide map projection, because it is a perfect ellipse where the aspect ratio is 2:1, it can be interrupted into two perfect circles. But please do not confuse the interrupted Molly-wide map projection with the orthographic map projection from the very beginning. There are two very different map projections. All of these circles are equal area, even if optically they don't really look like it, they are. Mathematically, you can prove it. Here's how you build it from scratch. First idea is that the Molly-wide map projection has an aspect ratio of 2:1, and it is an ellipse. So we know that the formula for the outer layer of the Molly-wide map projection is this. It has to be some variant of this. Do we know what y is? No. Do we know what n is? No. But in order to have an aspect ratio of 2:1, it has to be some variant of this. The second idea is that the total area of the map, if it's an equal area map projection, should be the same as the total area of the globe. We have the outer functions, and we're going to do 4 times the integral, and that will give us the area. And as you can see, if n equals r square root of 2, then that would be true for the Molly-wide map projection. That's why we're going to use n equals square root of 2, and from now on we've narrowed down that the x formula for the Molly-wide map projection is this. And now the third idea, the last one we need to discover exactly what the Molly-wide map projection is. All equal area maps that have strictly straight horizontal latitudinal line, they all have the same area for the same latitude. So, for example, we're going to compare the Molly-wide map projection to the sinusoidal map projection. The way we can represent the area for the latitude of the sinusoidal map projection is with this integral. And the way we do it for the elliptical map projection, well, we don't know, because we don't know how the latitude is defined. So we're going to build an equation, and that's how we'll end up finding what the Molly-wide map projection is mathematically. So I'm not going to waste time here solving these integrals. Here's what these integrals look like when they're solved. And as you can tell, we're going to define it implicitly. Here's what it looks though graphed. Since it's implicit, I think it's important to see what the function looks like. We're going to do a substitution, which will drastically simplify this implicit equation. So once we do this substitution, we end up at the very end with this, which is our very simplified implicit equation. And now we know that y is defined by the function, and we know that the function is defined by this. So we can just compare them and find that the y function that defines our Molly-wide map projection is r square root sine of theta, and theta is implicitly defined using this implicit equation, and we can tell that theta depends on phi. As for our Molly-wide map projection, we can now conclude that it is defined by either this or this for the x value and this for the y value. I kept the L of ellipse of earlier just because we defined it like that earlier. And theta is defined implicitly using this. Now I will add one thing. You may have noticed this is the only map projection so far that has no trajectory on it. And the reason is, mathematically, it's already complicated enough. It would be too complicated to go there. So you can just use the point generator formula anyways. That'll be all. Thank you.